Oscar Meza Tovar, and I'm a graduate student from the Earth and Environmental Science Department here at UTA. The title of my poster is Modeling Seasonal Thermal Stratification and Mixing Variability in a Subtropical Reservoir. My study focuses on Lake Arlington, a eutrophic reservoir in north central Texas which experiences monomictic mixing, meaning it typically mixes only once a year. It plays a critical role in water supply, recreation, and ecological health. Weekly observations since September 2023 help us monitor how this lake responds to seasonal and episodic weather patterns. So, we hypothesize that climate variability, especially changes in temperature and precipitation, would alter the timing and strength of lake stratification and mixing. Our objectives are: one, to quantify how temperature and mixing patterns evolve throughout the year; two, to simulate these dynamics using a one-dimensional thermodiffusion model; and three, to assess how mixing affects oxygen availability and water quality. So, to model evolution, we adapt Stefan's one-dimensional heat diffusion framework. We start with a basic uh, form of the heat diffusion equation, where capital T is temperature, lowercase t is time, z is depth, and k is the eddy diffusion coefficient. We then expanded this into a depth-dependent form to represent how mixing changes with depth and lake area. This is introduced by term AZ, so changes of area with depth. Finally, we incorporate external heat inputs, both from solar radiation and a power plant locally nearby, resulting in this final formula. Uh, this is where H is the internal heat from solar input, and QPP represents the thermal discharge from the power plant. We utilize lake bathymetry to calculate the area by depth and validating our results using weekly field observations. Atmospheric data were collected using a Kestrel 550, while lake conditions were measured using a YSI Pro Solo. So now to the results. We present three different sets of results. One is temperature dynamics, where we can see the observed temperature profiles show seasonal stratification in summer and full mixing from fall through spring. The one-dimensional model, shown below, captures general thermal trends well through it, though it underrepresents short-term variability compared to the weekly measurements. Now for thermal stability. We use Schmidt stability and H-crit to assess the lake's resistance to mixing. High H-crit and low stability in winter suggest full vertical mixing. In contrast, summer stratification shows shallow H-crit and strong resistance to mixing. And my third result, dissolved oxygen. We found that hypoxic conditions were observed in the bottom depths during their summer months when mixing was the weakest. And we see that the lake is well oxygenated through our winter months. Next, we move on to apparent oxygen utilization. So, AOU helps reveal biological oxygen demand and areas of restricting mixing. We do see a spike of this during our summer months, and then we see a really high spike during our winter months. This could be due to our low temperatures. Conclusions and future work. Our findings confirm that seasonal climate variability plays a major role in shaping the lake's thermal and ocean structure. The one-dimensional model offers a valuable tool for forecasting stratification dynamics, which are crucial for managing water quality and anticipating ecological stress. For future work, we plan to integrate stable oxygen isotopic data for better mixing diagnosis, expand the model to predict oxygen distributions more accurately, and eventually upgrade to a three-dimensional general circulation model for enhanced spatial resolution. Lastly, I want to acknowledge, in my acknowledgments, I want to thank the City of Arlington Parks and Rec, my advisor, Dr. Arnie Wingeth, and my field partner, Tom Wilson, for their essential support. Thank you so much. Have a wonderful day.